Somewhere in the universe, a microscopic bubble could be coming. It rewrites physics as it moves. This is called vacuum decay. Think unstable vacuum, and a lower one finally wins. If it happens, there is no warning and no pain. The wall races at light speed. You never see it. Still, odds seem tiny. Night air is still and the stars look perfectly normal. Then, without sound, reality flips like a light switch. Vacuum decay means the fields under everything find a lower energy. That lower state is called the true vacuum. We care because our vacuum hosts atoms, chemistry, and life. A different vacuum could break atoms and erase every structure. Quantum tunneling lets a tiny region jump into that lower state. That seed becomes a bubble of true vacuum. Its wall is a moving front where energy gets released. The wall accelerates and quickly approaches light speed. Inside the bubble, constants shift and forces take new values. Outside the bubble, nothing can resist the advancing front. Tiny test, imagine copper turning unstable the instant it enters. Every wire you know would vanish with no heat or debris. A bubble could begin smaller than a proton in empty space. In microseconds, it grows to mountain scale. In seconds, it spans continents and sweeps the planet. At light speed, it crosses one Earth radius in 0.02 seconds. No telescope sees it coming because light cannot outrun it. Bottom line, vacuum decay is abrupt, silent, and total. Zoom far beneath atoms to the Higgs field filling space. It gives particles mass by clinging to them everywhere. Metastable means our field sits in a valley, not the lowest. We care because deeper valleys change masses and destroy chemistry. Calculations track the Higgs self-coupling as energy rises. Quantum loops from the heavy top quark nudge that coupling downward. Past some huge scale, the effective potential can tilt below zero. Estimates place that scale very high, between 10 to the 10 and 10 to the 12 GeV. Then our vacuum has a lower neighbor across a potential barrier. Tunneling rate is set by a bounce action, basically barrier size. Big action means stupendously tiny probability per cosmic volume. With the Higgs near 125 GeV, we look metastable. The top quark around 173 GeV deepens the tilt. Crunch the numbers, and the lifetime dwarfs any meaningful timescale. Think longer than 10 to the power of 100 years. That beats the heat death by absurd margins, even with uncertainties. Example in real terms, far less than 1 decay per Hubble volume, so chances here and now are effectively zero for us. What to remember, metastable Higgs plus tunneling yields a near impossible event. Picture a spherical front sweeping across space like a tide. That front is the bubble wall where fields change state. You care because nothing outruns it, not even information. No signal can warn you since light cannot get ahead. The wall accelerates due to the energy difference across phases. Friction is tiny in empty space, so it keeps speeding. Calculations show it approaches light speed very quickly. A soap bubble expanding through a lattice of stars. Where it passes, stars are rewritten, not shattered into pieces. If a bubble formed near Pluto, Earth would have minutes. 1 astronomical unit at light speed takes about 8 minutes. Across the solar system, inner planets go in under an hour. Through our galaxy, the front keeps going. Disk width needs roughly 100,000 years. Galaxies do not stop it, and black holes cannot cage it. There is no safe bunker or clever shield anywhere. Net result, bubble dynamics leave no time and no escape. Deep underground, detectors hum and protons smash to glittering sprays. From these collisions, we measured the Higgs mass. It sits around 125 GeV. We also weigh the top quark, near 173. Those two numbers steer the vacuum story more than anything. You care because tiny shifts push us stable or metastable. Heavier top quark pulls the potential downward at high scales. Lighter top relaxes it and supports full stability. Calculations run couplings upward using renormalization group equations. They ask where the Higgs self-coupling crosses zero with energy. If it crosses, the lower valley exists behind a barrier. Then tunneling is possible, though fantastically rare in our parameters. Current best fits place us in the metastable wedge with comfort. Rule of thumb, small changes in the top mass matter a lot. Shift it by 1 GeV and the conclusion can flip. Concrete example, lifetime estimates exceed 10 to the power 100. That dwarfs an expanding universe lasting trillions upon trillions of years. So your calendar stays safe, barring extreme unknown physics. So the picture is, data favors metastability with absurdly long lifetime. Whenever this comes up, someone asks about particle colliders. Could a machine spark the fatal bubble and doom us all? Short answer, no, collisions cannot trigger vacuum decay. That fear misunderstands what controls quantum tunneling. You care because human experiments should not be existential risks. Tunneling rate depends on field energy spread over cosmic distances. Local blasts dump energy and often raise the barrier instead. Warm regions suppress tunneling, like heat discourages water from freezing. Nature has already run higher energy tests across the cosmos. Ultra-high energy cosmic rays hit Earth. Some reach 10 to the power of 20 eV. They strike our atmosphere far more often than collider events. Integrated over ages, Earth has taken around 10 quadrillion of them. Galaxies see even more, per star and per year. If such hits were dangerous, we would not be here. Common mistake is thinking energy equals reach in field space. The bubble seed needs the whole field to cooperate coherently. Two protons colliding do not reorganize the vacuum across kilometers. Bottom line, colliders are safe, and nature proved it repeatedly. Roll time back to the first split second after the Big Bang. Space inflated, stretching tiny regions into cosmic scales. If our vacuum were too unstable, inflation would end in patches. You care because patches would leave scars we could still see. Bubble collisions would imprint circles or warps on the microwave sky. We map that sky with satellites, finding exquisite uniformity. Temperature variations are about 1 part in 100,000. There is no clean pattern of concentric arcs or abrupt edges. That observation constrains how eager tunneling could have been. Too fast and we would spot the aftermath in every direction. Theory also links stability to inflation energy through gravity effects. High inflation scales can tilt the potential, changing safety margins. Current bounds still leave huge room, but avoid dangerous corners. Example, in real terms, no giant cold ring has been confirmed, so the early universe data quietly agrees with long lifetimes. Net result, our past does not hint at imminent decay. Pulsar timing arrays also see smooth backgrounds, not violent phase walls. Large-scale structure forms gradually, matching a mostly stable vacuum. Gravitational waves from bubble collisions have not been clearly detected. Altogether, observations push the risk toward vanishingly small. Above standard model energies, new ingredients may reshape the potential. Extra particles can bend the Higgs coupling back upward. You care because unknown physics could stabilize everything permanently. Supersymmetry adds partners that soften the top quark's pull. Heavy neutrinos from seesaw models can tweak running at high scales. Even gravity might add higher operators that lift the far valley. Physicists model this with a term like C6 times h to the 6. It is divided by m squared. Small positive coefficients can turn metastable into safely stable. Negative ones could worsen things, though data disfavors extremes. We do not know the signs yet or the exact scales. Colliders, cosmology, and precision tests nibble at these possibilities. A future lepton collider could pin the top mass more tightly. That alone would clarify where we sit on the phase map. Gravitational wave observatories might hear relics of early transitions. Dark matter discoveries would also hint at new stabilizing sectors. Concrete example, shift the top mass lower by 2 GeV. Many analyses then move us into the fully stable region. Conversely, a higher top pushes deeper toward metastability. What to remember, unknown physics still holds the final verdict. We started with a bubble that erases everything without warning. Now you know it is real theory, not mere drama. You also know the odds are astronomically low for us. That mix is oddly calming. Respect the universe, then carry on. If a bubble comes, we never see or feel it. Until then, physics keeps refining the numbers and the picture. If this sparked good curiosity, follow for more deep dives. I have a wild one on cosmic inflation waiting next. Thanks for watching, and take a slow look at the stars.